Hello, this is your instructor, Richard Collier Data, Unit 2 of ATM101 Weather and Climate of Alaska. This unit is about how meteorological information is presented and interpreted. In this unit, I present station models, surface air and upper level maps, and radar and satellites. This lecture supplements our textbook Weather, a Concise Introduction by Gregory Hakim and Jerome Patou. Science produces a lot of computational powers, can produce even more numbers, and it's easy to get trapped. However, as Richard Hamming noted in the 1960s, the purpose of computing is insight, not numbers. Insight into a problem depends on how a topic is presented. So with apologies to the many people credited with the following saying, a good picture is worth 1,000 words. In meteorology, we use maps to represent weather and climate. The map in this slide shows the weather forecast for Alaska by meteorologists at the National Weather Service in Anchorage. The forecast was made on Saturday, 17th of January 2026 for Sunday, the 18th of January 2026. The map shows Alaska, northwestern Canada, and eastern Russia overlaid with contours of pressure. Like contours of elevation on a topographic map, we see highs where there is a maximum in pressure, like mountains on a topo map. There are lows where there is a minimum in pressure, like valleys on a topo map. Over the Yukon Territory, there is a high with a pressure of 1039 hectopascal. Over the western Aleutians, there is a low of 979 hectopascals. The wind blows clockwise around the highs and blows counterclockwise around the lows. We also see fronts, the colored lines, and ridges, dashed black lines, that we will fully explain later. The map also shows shaded areas where there is cloud cover, green areas where rain is likely, and blue areas where snow is likely. We see that the rain and snow are associated with the lows and ridges. Station models are used to represent at a particular time. The station model can provide the following information: temperature, dew point temperature, wind speed, wind direction, cloud cover, significant weather, and pressure tendency. However, station models are usually simplified to avoid information overload and clutter on the maps where they are presented. In this station model, cloud cover is in a circle at the center that also marks the station location on a map. Temperature is in the upper left, significant weather in the center left, dew point temperature in the lower left. Pressure is given in the upper right. The wind barb points in the direction wind is coming from, and wind speed is marked with barbs and pennants. The small barbs indicate wind speeds of 5 knots, long barbs 10 knots, and pennants 50 knots. Reading this model, we see overcast because the circle at the center is completely black. There is light rain, as evidenced by the 2 dots in significant weather. The wind is coming from the northeast with a speed of 25 knots or 46 kilometers per hour or 27 miles per hour. The temperature is 12 degrees Celsius or 54 degrees Fahrenheit, and the dew point temperature is 10 degrees Celsius or 50 degrees Fahrenheit. This map shows the location and their station data across the United States, northern Mexico, and southern Canada on the 20th of February 2014 at 1800 or 6 p.m. UTC. Looking at the University of Chihuahua, the station model. For Chihuahua University Organization Site 62250 at 28.6 degrees north and 106 degrees west, we have a pressure of 1,001 hectopascals, a wind speed based on the small barb of 3 to 7 knots, or 5.5 to 13 kilometers per hour, or 3.5 to 8.1 miles per hour, a wind direction from the north, so northerly, or towards the south, southward, and a temperature of 23 degrees Celsius or 73 degrees Fahrenheit, and a dew point temperature of -1 degree Celsius or 30 degrees Fahrenheit. In this case, the dew point temperature is much lower than the actual temperature, indicating it is very dry with less than 5% relative humidity. This is consistent with Chihuahua being a hot, arid desert climate. We can also represent the temperature contours are called isotherms, lines of equal temperature. Following our intuition, higher temperatures are colored red and colder temperatures are colored blue. We can now identify areas of colder air where the temperature is relatively uniform, called cold air masses. We can also air where the temperature is relatively uniform, called warm air masses. And finally, we can identify where the temperature changes rapidly. These areas where the temperature isotherms are packed close together are called fronts. Weather at mid and high latitudes greater than 6 degrees is largely due to the motion of air masses. When air masses meet, there is an abrupt change in temperature and humidity and density. This boundary is called a front. Weather happens along fronts as the colliding masses of air cause air to rise at the front and cause formation of clouds and precipitation along the front. In this figure, we see a cold air mass moving toward the southeast and a warm air mass moving to the northwest. The boundary of the cold air mass is a cold front plotted as a blue curve with blue arrows pointing in the direction of motion. The boundary for the warm air mass is a warm front plotted as a red curve with red semicircles pointing in the direction of motion. We saw in the lab that typical changes of pressure in the horizontal are about 60 hectopascals, from a low of 979 hectopascals to a high of 1040 hectopascals over distances of thousands of kilometers. Pressure changes much more rapidly in the vertical, about 10 hectopascals every 100 meters. Thus, stations at different elevations will support systematic changes in pressure due to changes in elevation. Stations at higher elevation will measure consistently lower pressures than stations at lower elevations. To map horizontal variations without contamination by elevation, we compute the pressure at each station corresponding to the pressure at sea level for that location. We calculate the pressure at sea level that corresponds to the station pressure at the station altitude. The simplest correction is to add 10 hectopascal or millibars for every 100 meters of elevation. In this slide, we see that station 100 meters and measures station pressure of 952 hectopascals or millibars. To obtain the sea level pressure, we add 60 hectopascals, 10 millibars for every 100 meters, and there's 600 meters in 600 meters, to the station pressure to estimate a sea level pressure of 1012 hectopascals. For station level, there is no correction, and therefore the station pressure of 1000 hectopascals or millibars is the same as the sea level pressure of 1000 hectopascals or millibars. Once the sea level plotted as a contour map, where the contours are called isobars, lines of equal pressure. Again, as we saw on the temperature maps, we see areas where isobars are both spread far apart and packed closely together, corresponding to areas of shallow and steep pressure gradients. Combining the contour map of pressure and temperature gives us insights into the weather conditions, as we see how specific pressure features correspond to specific temperature features. Such a map is called a synoptic or together view of the weather. While highs and lows are defined by the pressure contours, ridges defined by the pressure correspond to fronts that are defined by temperature and the boundaries between air masses. Ridges and troughs are analogous to the ridges and valleys in topographic maps. At higher levels in the given altitude level, and then map of pressure at that altitude. However, meteorological convention is to work at levels defined by constant pressure and determine the variations in altitude at that pressure. For example, the 850 hectopascal level is typically found at an altitude of 1.5 kilometers or 0.9 miles, while the 500 hectopascal level is found at about 5.5 kilometers or 3.4 miles. The use of pressure levels reflects the tradition of direct measurements of pressure by radiosondes and many satellites. The variation in altitude of pressure surfaces also reflects variations in temperature between that pressure surface and the ground. For a given pressure, a volume of gas will be larger for a higher temperature than for a lower temperature. Thus, a surface will be at higher elevation over warmer air and lower elevation over colder air. The local max called ridges and the local minima are. Thus, ridges are associated with warmer air with colder air. The station model for upper speed and direction and altitude in decameters, or tens of meters. Decameters are chosen as pressure altitude changes are not significant to 10 meters, and so 1 meter is overly precise. Furthermore, the use of decameters rather than meters allows for shorter numbers to be printed on the station model and less cluttered maps. The 500 hectopascal station model shown here reports a temperature of minus 23 degrees Celsius or 9 degrees Fahrenheit, an altitude above mean sea level of 550 decameters, which is equivalent to 5,500 meters, 5.5 kilometers, or 3.4 miles, a wind speed of 68 to 72 knots, equivalent to a wind speed of 125 to 134 kilometers per hour, or 78 to 83 miles per hour, and the wind direction is west-northwesterly. So coming out of the west-northwest direction, about 290 degrees east of north, or you can think of that as a wind headed toward the east-southeast, so an east-southeastward wind. Radars send out pulses of radio particles in the air, both ice particles and water droplets. Cloud particles and gaseous atoms and molecules are too small to be seen by the radar. The strength of the radar echoes increases with precipitation, while the time of flight for the echo to and from transmit to receive gives the range to the particles. A radar can scan in altitude and azimuth and map out the location of precipitation in range and angle from the radar site. Precipitation is found in bands. Two more advanced radars are also used in meteorology: Doppler radars and polarization radars. Doppler radar can detect the frequency shift in the echo signal due to the motion of the raindrops and thus estimate the speed at which the raindrops are moving toward or away from the radar. Polarization radar polarizes electric fields, where the electric field of the radar pulse is oriented in the horizontal or the vertical. The return signal will have some of the electric field shifted to the other polarization, and the amount of this change increases as the particles become less spherical and more irregular. Thus, polarization radars can be used to discriminate between raindrops, which are largely spherical, and snow ice particles, which are more irregular, and thus identify melting layers, where snowflakes turn to raindrops while falling. Satellites. A weather satellite, TIROS-1, was launched by NASA on the 1st of April 1960. TIROS, the television infrared observation satellite, had two television cameras that recorded the view of the Earth and transmitted that data back to Earth. Satellites today are more sophisticated, using a wide variety of sensors that detect not only the visible radiation reflected by the sun, but also infrared and ultraviolet radiation to measure temperatures, winds, and composition of the atmosphere. Satellites can view the Earth from two types of orbits. In geostationary orbits, the satellites sit 36,000 kilometers from the center of the Earth. Geostationary satellites rotate with the Earth and stare down on the same area of the Earth day after day. Measurements from a constellation of satellites parked at different longitudes can be combined to give an instantaneous global picture of the atmosphere. In contrast, polar orbiting satellites are at lower orbits, about 800 kilometers above the Earth's surface. As the satellite orbits, the Earth rotates from west to east beneath the satellite. The satellite records a series of swaths of the atmosphere that move from east to west. Typically, the satellite makes about 14 orbits per day and provides a composite view of the atmosphere over the course of the day, where each longitude is measured at the same local time. Geostationary satellites provide an instantaneous view of the whole atmosphere at lower resolution than a polar orbiting satellite. Polar orbiting satellites provide higher resolution images of the atmosphere over 24 hours of observation of the whole atmosphere. While the geostationary satellites provide good views of the tropics, where they are overhead, their view of the polar regions is limited, and polar orbiting satellites are essential for meteorological observations at high latitudes. Satellites make measurements visible, infrared, and the water vapor bands. The combination of the three measurements provides insights into the clouds that are present. For example, the cloud in Area A in the visible channel is bright in infrared and bright in water vapor. Thus, the cloud top is colder and higher in the atmosphere with a large amount of water vapor, and the cloud has significant vertical extent. The cloud in area is dimmer in the infrared and water vapor. The top is warmer and lower in the troposphere with a smaller amount of water vapor, so the cloud is lower in the atmosphere with less vertical extent. Finally, in area C, form clouds, while the infrared image shows variations in temperature and cloud top height, and the water vapor image shows significant variations in water vapor. This serves to remind us that visible observations by themselves are not sufficient to adequately describe the clouds for weather forecasting purposes. Composites of geostationary global patterns. At mid-latitudes, from 30 to comma-shaped patterns of clouds associated with low-pressure systems. In the subtropics, to the US Southwest, North Africa, and Australia, there is a general absence of cloud due to descending air motion at these latitudes that inhibits cloud formation. In the tropics, there are patchy clouds due to convection. The polar orbiting satellites, as they are 30 times closer to the Earth's surface than the geostationary satellites. Again, the same pattern of clouds associated with the mid-latitude cyclones, the cloud-free subtropics, and tropical convective clouds is observed. The new geostationary provide a higher resolution view of the atmosphere. They measure images over a wider range of different wavelengths as well as shadows to sharpen the images. This slide shows a very high resolution image of the clouds associated with a summertime cold front in Texas. These observations can support high resolution forecasts of precipitation, which varies greatly over relatively short distances. Finally, we look at the weather. December 2025 was the coldest month in interior Alaska since January 2012. In January 2012, we kicked off ATM101X as an outdoor observing course, and students made measurements at minus 55 degrees Fahrenheit or minus 48 degrees Celsius. This past December was the coldest December since 1980. We present the daily temperatures for December 2025 from the Alaska Climate Research Center at UAF. The green bars show the range of temperatures each day. The gray band shows the normal range of temperatures. The red curve shows the record high temperatures, and the blue curve shows the record lows. The columns along the bottom show daily precipitation, and we see that precipitation is associated with higher temperatures. The map across Alaska on the colder days. On all these days, there is a dominant high-pressure system over interior Alaska with generally clear skies. On several days, there is a low pressure system butting up against the high with a strong pressure gradient between the two systems. These gradients would result in high winds in the region of these gradients, but we notice that the lows are not sufficiently strong to push the high pressure system out of interior Alaska. Our summary and takeaways for station models provide a graphic summary of station measurements. Surface temperature maps are designed to show weather features including fronts and air masses. Surface pressure maps provide direct characterization of weather systems, the highs, the lows, the ridges, and the troughs. Composite temperature and pressure maps provide more insight into the weather as they identify air masses associated with the highs, lows, ridges, and troughs. Upper level maps show the height of constant pressure surfaces. Station models for upper levels include height of the pressure level. Pressure maps use the concept of elevation, with highs, lows, ridges, and troughs mirroring mountains, valleys, ridges, and valleys. Satellites yield visible infrared and water vapor images that are combined to determine the weather associated with fronts. Geostationary and polar orbiting satellites provide different views of the Earth with different trade-offs. Polar orbiting satellites are particularly important in supplementing geostationary satellites in the polar regions. In our next unit, Unit 3, we will explore the origin, composition, and structure of the atmosphere. Thank you for your attention.